Okay, so this is a final example on circular motion. This is to do with the banked curve. On your handout sheet is number 8, and it involves a banked curve where you have a car with a specific mass of 1,100 kilograms. Notice it says it's a frictionless banked curve. That's always our assumption. There's no friction. Essentially, from a practical point of view, as an engineer designing a highway curve, you would design it as if it's completely icy surface and there is no friction, that there's never a possibility of someone flying off flying off in the tangential to the direction of motion. Okay. Anyway, so there's sort of 4 parts to the question. What force is causing the centrifugal force? Draw a free body diagram, solve for speed, and then talk about what does mass have to do with that speed. So if you're the engineer designing this bank curve, do you need to take into account sort of what a very heavy vehicle can do, or can you do a general case, or do you have to consider the lightest vehicle for the safest case? All right, so let's move on to part A, what force causes the centrifugal motion, and we talked about this a bit already. My picture, centrifugals towards the center. Here's my normal. Here's my coordinate system where I have x and y. Here's my angle. And FC equals center seeking. And the center seeking force, the only center seeking force, is a component of normal. And what it would be, keeping in mind from previous, that Fn is mg by cos theta. The x component of that would be Fnx. And if I was going to be more specific, then besides just saying the x component, I could then say Fnx is F and sine theta because it's opposite the angle. So it's mg or F and x is FC equals mg. Okay, and that would be the answer to part A. What is the force that provides the acceleration? Well, it's the x component of normal, which is mg tan theta. In part B, it says draw a free body diagram and determine the normal force. So again, x, draw it. This is really asking us to figure out that relationship. Okay. Okay. So here's my free body diagram. Remembering that these are not forces in and of themselves. These are components of my normal force. This is Fn. So the only 2 forces acting are normal force and gravity. To find what normal force is, or to develop that relationship of mg by cos theta, we would say that up equals down. So Fny must be equal to mg. That's where I came up with this. And so therefore, looking at the triangle this way, I've got mg here, and I've got theta here, and Fn here. I can say that mg by Fn is cos theta, or Fn rearrange And it wants us to actually figure it out for this particular car, so we will. FM equals 1100. Mass of my car. And K over, oops, 19-degree angle. And you can put that into your calculator to solve for that then. Okay. In part C, let's borrow one. Okay. In part C, it asks us to find the speed that it could travel safely. But really that's saying such that my centrifugal force is equal to my x component of normal, which we already determined was Fc equal to mg tan theta, or mv squared over r. Masses cancel, which by the way gives us our answer to part D. And you can rearrange and solve for E to be equal to 17 meters per second. Okay, remember that we know R is 85 meters. We know the angle, we know everything we need to know to find the speed 17. Just to jump ahead to D, and the answer is mass has no effect. We cancel mass out of the equation. It doesn't matter if you had a 100-pound car or a 10,000-pound car, it wouldn't affect your answer for speed. So mass has no effect. Which might be misleading or against your intuition, right? Just like we often think that heavier items fall faster, it might be easy to think that a heavier item would have more sticks to the ground and therefore it would go at a faster speed. But taking into account the effects of centrifugal acceleration, it's just not the case. Okay, that's just an extra example on working with banked curves, and